So these are the notes for part 1 of the atom. I know on the calendar it said parts 1 and 2, but on Friday we just did part 1. You can see at the top that thanks to our good friend Democritus, we now have the lovely term atom for our fundamental particle of matter. Democritus was mentioned in the article that you should be reading, as well as the video that we saw in class on Thursday. The progression of the atomic theory, they philosophized back in the day, but then through scientific experimentation and investigations and data collection, our atomic theory has advanced throughout time. A couple of different laws that were really fundamental in setting up our first major atomic theory through John Dalton appear here below. The first one is the law of definite proportions. And you can see here that it states that two samples of a given compound are made of the same element. Hold on, let me resize this. Okay, that's a little better. Two samples of a given compound are made of the same elements in exactly the same proportions by mass, no matter the sizes or sources of the samples. So this was kind of important because if you've got water, a drop of water in Germany, a cup of water in England, water coming from the well in America, or water from the ocean in between, no matter what, water is made of the same elements, hydrogen and oxygen, in the same proportion by mass, no matter where it is. So that was kind of important. Next up is the law of conservation of mass. And this one you may have heard of from 9th grade or before. But it says there that whatever goes into a reaction comes out. The mass of the reactants in a reaction equals the mass of the products. And you can see this on the particle level. A single hydrogen molecule plus an oxygen atom will give you a water molecule. And you can see those ugly numbers, but if you try it on your calculator, 3.348 times 10 to the negative 27 plus 2.657 times 10 to the negative 26 will equal 2.992 times 10 to the negative 26. Our good friend the mole will be showing up in chemistry, and we'll be using molar masses, and that's what you see below. So when I say 2 grams of hydrogen plus 16 grams of oxygen will make 18 grams of water, you just see that the mass of the reactants equals the mass of the products. This is why we balance equations in chemistry. When we start doing the math of chemistry, stoichiometry, then we will see why it's important to have that chemical accountability, knowing what goes in must come out. Our last law is the law of multiple proportions. And you see here, this chart that I put there, this chart shows the different compounds that nitrogen and oxygen can make, and there's many others. But focus on that formula column. You see that nitrogen monoxide, nitrogen dioxide, they are simple whole number ratios, and those are the types of compounds that are formed when our atoms get together. The math can get complicated. We won't do that in this class, but you can see over here that in nitrogen monoxide we have a 1.14 gram of oxygen to nitrogen ratio. Nitrogen dioxide 2.28 to 1. So that's good. That's not the simple whole number ratio we're talking about, but you can see 1.14 to 2.28 is exactly double. And if we had nitrogen trioxide, it would be triple. So those whole number ratios are important. And again, all of this led us to Dalton's atomic theory, which from 1808 was pretty, revolutionary. And we can see, you're welcome by the way for the fill in the blank. So all matter is composed of atoms. Thank you, Democritus, we kept your word, which cannot be subdivided, created, or destroyed. Number 2 and 3 sound a little like no duh, but they're pretty important. Atoms of an element are identical in their properties, physical and chemical, but different from other elements. So chlorine atoms are different than lead atoms. Again, sounds like no duh, but up until then, we thought that all of the atoms were these little tiny indestructible spheres, and they were just the same kind, and we put them together in different ways and different amounts to create stuff. But through experimentation, we said, no, there's different types of atoms out there. There's chlorine atoms, and iron atoms, and oxygen atoms, etc. Number 4 is that law we were just talking about, that we see that the elements combine in simple whole number ratios to form our compounds. And then lastly, we see here that in chemical reactions, we can combine, put the atoms together to form compounds, separate, we can break them apart, decomposing the compounds, rearranging them in space, but we can never create or destroy them. So that's pretty good for Dalton back in the day. You know, didn't really have running water, barely had electricity, all this kind of stuff, so it was pretty revolutionary. And when we look at what is put together this whole theory, some of this is really still very true today. All right. Blue. Atoms is what we still call the fundamental particle. Matter is composed of these atoms. And water is H2O. That is a compound and it still has simple whole number ratios. When we run chemical reactions, we are combining or separating or rearranging the atoms, so that is definitely true. And our element atoms are different. Atoms of chlorine are definitely different than atoms of lead. So that's quite a bit for still being true today. The other parts here that aren't quite true anymore are these parts, subdivided. Are the atoms the smallest things? No. We know that inside our atoms we have protons and neutrons and electrons. And if you've read into that article at all, there's even smaller things, quarks, leptons, muons, beta particles, positrons. Yikes. But that's beyond the scope of this course. But we do know now that there are things smaller than the atom. Can we create atoms? Yes. On our first test, you wrote a symbol of an element that was a gas, you wrote a symbol of an element that was a liquid, and you wrote a symbol of an element that was man-made. We can create elements in the laboratory. Can we destroy them? Sure. Atomic bombs, splitting of the atoms, getting a lot of energy. Same with nuclear power plants. That's where fission is happening, the splitting of atoms. So this creating and destroying stuff is not true anymore today. The last part is that word identical. And as we'll see on Monday and with our lab on Tuesday, not every atom of an element is exactly the same. Not every oxygen atom on our planet is identical. There's that lovely word called isotopes that we will explore further that explains how they're not completely identical. But that's a great theory. It really was. And like all great theories, scientists have two choices. Repeat it and repeat it and repeat it and turn it into a law, or find out what's wrong with it. And that's what our first guy did, Mr. Thomson. He discovered that there was more to this atom. By using a cathode ray tube, he discovered our first subatomic particle, our particle smaller than the atom, the electron. Okay, this beam of particles was going by, and he was able to calculate the mass of those particles. And when he did, it was way smaller than what was expected. They thought the smallest thing on the planet was the hydrogen atom. But this calculation said that's whatever's in that beam is 2,000 times smaller than a hydrogen atom, the electron. And so we figured out it was negative by using a magnet. So when you have, from that video the other day, we have charged particles, and here with this magnet, we see that the beam is being deflected away. So since the beam is negatively charged, as we now know the electron is, this magnet must be negatively charged because it's pushing the beam away. Like charges repel, opposite charges attract. And so Thomson came up with his model of the atom with this negative electron in it. And next up was Mr. Rutherford. Mr. Rutherford had a gold foil experiment that we saw in that video. He was shooting alpha particles through some very thin gold foil. He expected them all to go through. Well, they didn't. They didn't all go through. And so some of them got deflected away. The particles were positive. Again, like charges repel, so when the particles came in, they hit something else positive and left. And so that's how he discovered the nucleus. Our atoms have a very small, very dense, positively charged nucleus, and we now know that this positive charge comes from the proton. To go abstract again, like chemistry likes to do, if I took a carbon atom, let's say, and I blew it up to the size of Cleveland Brown Stadium, as we heard in the video, this term, the electron cloud. The electron cloud would be as big as Cleveland Brown Stadium. The nucleus would be the size of a marble, floating in the middle, with a mass of like 250 tons. Very, very large amount of mass in a very, very small space. Very dense. And we'll talk about that more later. But for right now, Thomson discovered some negative stuff. Rutherford discovered some positive stuff. But together, we still know that all atoms are electrically neutral. However much positive stuff is in the atom, there has to be the same amount of negative. Yes, there's ions and things with charges that we'll talk about later, but all atoms are electrically neutral. And in addition, the last missing piece was the neutron. Not too long ago, about 80 years ago, Sir James Chadwick discovered the last missing piece, the neutral neutron. Now I have massive there because they were missing part of the mass of the atom. They knew how much the electrons weighed, they knew how much the protons were, they didn't add up. And so they finally discovered this neutron, which has about the same mass as a proton, but with no charge. Again, like charges repel, so all those little tiny protons in the nucleus, they don't want to be next to each other. But when you put the neutral neutrons in, kind of keep the peace, and so we keep the nucleus intact. And then the last little chart at the bottom, okay, some other classes you can get in some advanced calculations using the Coulombic charge, or maybe those ugly mass numbers like we talked about over here, 10 to the negative stuff kilograms. But you should definitely know and remember that an electron has a charge of -1, proton +1, and neutron 0 for neutral. Those are the common charges we'll deal with. Alright, that pretty much wraps that up, and we'll pick it up in class later. Thank you.